Okay, so last time we got a few results. One is proposal by Feynman, the Feynman path integral, and we used Schrodinger theory to compute the same quantity, and the structure was different. So let us write down that results. One is Feynman path integral. We are calculating a matrix element, say if I, which is a shorter notation for the matrix element that we wrote down earlier, a different notation. It's a simpler notation I'm using. This is given by this path integral, where you path integrate e to the power I by h bar is functional. While calculating s, s is integral dt times Lagrangian, which depends on this paths. And therefore, you have to specify a boundary condition, and this boundary condition conditions are given by, say, let me put it here. So I to f I to f, this is equation 1, where I'm using some shorthand notation. This I actually refers to xi at ti. Similarly for f, and this I is it means that these are paths with the fixed boundary where x at ti is equal to xi, as given by the state on the left hand side. That specification of the state on the left hand side appears as a boundary condition for the paths over which we are integrating. Okay, and this is a configuration space path integral. Okay, so the comment is that configuration space path integral, and this is an obtained by through an ad hoc suggestion following Dirac's intuition. So it's an ad hoc suggestion following Dirac's intuition. And the other result which we derived, that is derived from Schrodinger theory. The same matrix element, if I, is given by dx dp exponential I over h bar integral dt ti to tf px dot minus h x dt where maybe I will have a convention, not sure if that is needed. Yeah, let me write it not xp but pxt. It doesn't matter, but So where h p x t is given by the matrix element of H between P and X eigenstates divided by Px overlap. And in both the cases, so this is in both the cases, your the path integral measure is proportional to product over say I equals 1 to n minus 1 dxi, and dp is proportional to I equals 0 to n minus 1 dpi. This, if you remember the operational definition where n goes to infinity. And these proportionality constants, these are constants that do not depend, constants independent of paths. Okay, and of course this is a phase space. This is a phase space, or sometimes called Hamiltonian. Hamiltonian path integral. Right? So these are the two results we have. So number 2 question is that what is the relation between these two? So so question is how to go from 2 to 1. Okay, and we will be answering these questions in 2 steps. In case 1, I will describe 2 cases. In case 1, I will take a specific form of the Hamiltonian, which is standard and which will have wide use. And in that case, we will see that this Hamiltonian path integral exactly gives you the configurations space path integral. You can just get this form directly by doing the calculation from here. If the Hamiltonian is of certain standard form, and that standard form will be of a lot of use for us in field theories. The other case is a more general case where Hamiltonian is not of that particular form, in which case this result, this is not directly same as this. There are certain modifications, but the modifications have specific properties. The goal will be to figure out what those properties are. So let us start with case 1. Case 1 is the case where momentum integral is Gaussian. So Gaussian momentum integral. So this happens when the Hamiltonian, this is the case when the Hamiltonian is given by p hat square by twice m plus v x hat. Okay, and this gives you that function h p comma x function to be exactly the classical Hamiltonian that we are familiar with. Okay. Just a moment. So in this case, if you calculate the matrix element, if I your first so you have dx dp, then exponential I over h bar integral dt ti to tf, and you just look at this px dot minus hpx. So that is px dot minus hpx means p square. So let us set m to 1, which can be recovered later by dimensional analysis, not a very big deal. And so we set m to 1 for the time being. Now we have to calculate this. Because of this form of this Hamiltonian, the momentum integral is basically e to the power p square, quadratic and linear piece. So this is a Gaussian integral, and the trick to do this integral is to complete the square first, because this is a p square, this is a p, so you can complete the square. So only this part, minus p half p square plus px dot, this part can be written as minus half p minus x dot whole square plus half x dot square, right? This is what means by completing the square. And then if you use this form, you can define p minus x dot. This is like a shifted momentum. It's a new variable, say q, right? You make changes of variables while doing integration. This is an example of that. P minus x dot, let us call q, and as a result, dp is same as dq, because x dot is just constant, to be treated as a constant when you calculate this differential. Okay, so combining all of this, what one gets is, for the matrix element, is integral dp is same as dq, and then you see this has two terms. One is minus half q square plus half x dot square. So minus half q square can be extracted, everything else is x dependent, so this can come out. So that is e to the power minus I by 2 h bar integral dt ti to tf q square, and then the rest is the x integral, e to the power I by h bar integral dt ti to tf half x dot square minus vx. This portion is totally independent. This is independent of x of t, x path integral, and therefore can be absorbed, therefore can be absorbed into the definition of measure tx. It's an overall constant. So, so this is integral dx. Okay, e to the power I over h bar a6. That's Feynman's form, and you get that exactly.